Problem number 16. Consider the vector field F with this formula right here. There's a curve C with this parametrization given here. And so we're supposed to use Stokes' theorem to find the circulation of F around that curve there, oriented counterclockwise and viewed from above. So let's write out. We want to find the integral of f dot dr around this curve. So the first thing to realize is that this is actually a problem, in principle, we could do in a straightforward manner. Why is that? So we have our vector field, we have our parametrization. We could just treat this as a section 16.2 problem, and here's our parametrization, take the derivative of our parametrization, substitute our parametrization into f, and integrate, take a dot product, I guess, first, and then integrate. And so that would definitely work here, although some of the calculations become a bit tedious. There will be some difficult trigonometric integrals to evaluate at the end of it, the kind of thing that would be a standalone problem in a Calc 2 class at the very end. And so we want to do this in a different manner. We want to do it in the manner that we are told to do here. So it says use Stokes' theorem. So if we see the words here, use Stokes' theorem, we know that we have to rewrite this as a double integral over some surface S here, and the integral is going to be of the curl of f dot ds, where what is S? What is our surface S here? Our surface S is this region inside of our circle, right? More of an ellipse, I guess. Tilt the ellipse here, oriented going upwards. The upwards orientation on the surface would correspond to being oriented counterclockwise around the boundary there. Okay, so this is our task to do. We want to compute this surface integral. So a couple things that we have to do here. One is that we need the curl of f. Let's go ahead and compute the curl of f. So I hat, j hat, k hat, partial derivative with respect to x, y, and z. And then we write down the entries here, 2xy squared, 2x squared y, and 2xy squared. Okay, so what do we get here? The first entry is going to be the partial derivative with respect to y of this, which is 4xy, minus the partial derivative with respect to z of something that doesn't depend on z, so that will be 0. The second entry is the partial derivative with respect to z of 2xy squared, that's 0, minus the partial derivative with respect to x of 2xy squared, so that will be minus 2y squared. And then the final entry will be the partial derivative with respect to x of 2x squared y, that is 4xy, minus the partial derivative with respect to y of 2xy squared, that's also 4xy. And so those will cancel out, and we're left with 4xy, negative 2y squared, and 0. Okay, great. We have the curl here. Next thing that we need is we need to parametrize this surface here. And so the thing to realize about this surface is that the surface S, it lies in the plane y is equal to z. How can we tell that? So first, the picture is hinting to us that this lies in a plane here, and we can further see that in our parametrization, the y component is sine t, the z component is sine t. So along this curve here, y is always equal to z. And so then we want the flat disk inside of that ellipse here. And so everywhere on that surface, y is still going to equal z. So we can parameterize our surface, r of xy, as x comma y comma y, because z is equal to y here. With bounds, x squared plus y squared is at most 1, because the boundary lies, the projection of the boundary into the xy plane is, well, x is cosine t, y is sine t, so that'll just be circle of radius 1. So that's our region here that we're integrating over. To find a normal vector, so partial derivative of this respect to x is 0, and that's the negative partial derivative of this respect to y is negative 1. Really, there's a negative sign on there as well, but negative 0, 0, and then 1. So here's our normal vector, and note this does correspond very nicely. If we move that y to the other side, we'd have negative y plus z is equal to 0, and we can see that 0 minus 1, 1 is a vector normal to this plane. Okay, so at this point, we have our normal vector, we have our curl. We would then need to substitute our parameterization for our surface into the curl of f here, but the only change would be replacing z with y, and there's no z's here. So we can just go ahead and do the dot product of the curl of f with 0, minus 1, and 1. So this dot product, this will give us 0 plus 2y squared plus 0. So our answer is going to be the double integral over s of the curl of f dot ds is the double integral over the region x squared plus y squared is at most 1 of 2y squared. Okay, we want to integrate this. It's in the region integration is filled in circle in the xy plane. Let's convert to polar coordinates. Theta will run from 0 to 2 pi. R will run from 0 to 1. And so this will become 2. Y squared will become r squared sine squared theta. And then there's one more factor of r that we throw in from the Jacobian. And so this is what we have to integrate. We can move that 2 out in front. Integral of theta will, I guess we have to, let's factor this as integral from 0 to 2 pi sine squared theta d theta times integral from 0 to 1 of r cubed dr. And so I have 2 times, this gives us pi, and this gives us a quarter. So the final answer here is pi over 2.